have to record today. I'll record anyways, just to be safe. Okay, this table is gonna collapse. Anyhow, so let's get started. In the last class, in particularly for example 1, actually it's not here anymore. I'll talk about it during example 2 then. It's related to whether we deal with effective stress parameters or total stress parameters. But this is going to be a long example, so we'll get to do this several times over and over again. So for replacement design, we will look at how to design for all 4 mechanisms that we discussed. We did not go into detail into each calculation method, so we'll do that here, and I'll try to explain the steps to you along the way. Maybe I'll point out some basic geotechnical knowledge that you should know as well, in case there's some of you preparing for interviews lately, I think. So this is going to be a long example, it's fine. So here we have a square concrete footing, has a nominal dimension of 1 meter. So that's just the footing, it's not the replacement zone, okay? The replacement zone is actually a bit larger, right? It's 2 meter by 2 meter. The footing is this one here. The replacement zone is underneath. Now, notice one thing here. For this interesting shallow footing, I did not give you the dimensions of the thickness of the footing. So what does that mean? If you have to calculate the weight of this footing later on, you're going to have to make some assumptions because we didn't give you the precise dimensions of this footing, which is fine. We'll talk about that. So in this example, you're given the dimensions of your replaced zone, or it's 2 meters by 1 meter in height by 2 meters into the page. So you know that you don't have to calculate the size, but you probably have to do some factor of safety checks. Now, typically in design practice, the factor of safety required for bearing capacity or to check against bearing capacity failure is 3. We typically adopt the FOS of 3. And it's mentioned here in the question. So we need to check the 4 modes that we talked about in the preceding slides. For 2 cases, we'll look at drained and undrained. I'll talk about what parameters we should use, what parameters you can use, what assumptions we made. So we'll talk about that in detail. You're given 2 unit weights here. You know the unit weight of the soil just above the water table is 18 kilonewtons per meters cubed, and anything submerged is 20 kilonewtons per meters cubed. Interestingly, this question gives you a very unique concrete weight. Instead of 24, they decided to go for 23.6. That's fine, we'll use 23.6, and then we have to check short-term and long-term settlements, or conditions in the question. So we know we have to look at total stress and effective stress analysis. That's about it. So let's look at this question and dive in together. So we need to break this up because it's going to be a very lengthy question. The first thing we need to assess is, without doing excavation and replacement, if it was just the in situ soft clay, would the shallow footing survive? Or by survive, I mean, will you be able to obtain a factor of safety of 3? We have to check that first. And if we cannot obtain a factor of safety of 3 for bearing capacity, then we have to replace. And by looking at the question, you probably can guess we need to replace anyways, right? Because it's already been replaced. And after we replace, we have to check for all 4 failure modes that we discussed in the previous slides. And the 4 failure modes are essentially shown in the red, listed 1, 2, 3, and 4. And we do have to check for undrained and drained conditions. This is standard in engineering design practice. We usually carry out total and effective stress analysis, and we take the smaller of the 2 to be conservative, to be on the safe side, right? So that's what we'll do in the following steps. So the first step is to calculate the net bearing pressure. So if if you flip from previous slides, you'll see that we can calculate the net bearing pressure as follows. So we apply a load on the footing of 150 kilonewtons. And remember here, we don't have the size, detailed dimensions of the footing. If you look at the bottom here, we don't have this dimension, we don't have this dimension. So what's the safe way to deal with this? Well, let's just assume that this is just one monolithic concrete block. So we know that this is a 1 meter by 1 meter by 1 meter block. Why can we assume this? Because it's conservative, right? It's a heavier load anyways. So we can say that the concrete block weight of footing, that's what WF stands for, is 1 meter by 1 meter by special unit weight of concrete. Instead of 24, we're given 23.6. And the area of the footing, A subscript F, is just 1 meter by 1 meter, right? Because we want the net pressure, we have to deduce or deduct the effective pore pressure. So we know that the water table is about 0.4 meters tall, just above the base of the footing. And we know the unit weight is 9.81 or 9.8. And we have our net bearing pressure. So why is this net bearing pressure important? Well, this net bearing pressure is somehow the value we'll use to check for factor of safety later on. So that's the first step done. The next step is, if I did not carry out replacement and I just put this footing onto very soft clay, what do we expect? Is it going to fail? If it fails, then we have to do replacement. If it doesn't fail, then we stop. End of question, right? So, the ultimate bearing capacity in situ soil is, so we can take our bearing capacity equation, generalized form. Previously, we have our cohesive components, we have our cohesive shape and depth factors, we have the unit weight component, the unit weight depth factors plus the overburden shown as effective here. I'll explain why later. So the effective overburden So we know that the effective burden at the base of the footing is 15 kPa. Now, what happens if you calculate the total overburden? Well, then you wouldn't cater for effective unit weight, right? You would just use 20, and you get a slightly larger effective overburden. Now, do bear in mind that if you remember from our drawings, when we push down this footing, what happens to these blocks underneath? Well, they want to squeeze upwards, right? So what is the overburden we're talking about? The overburden is this here, this thickness of soil. There's some pressure here, pushing the block back down to resist bearing capacity failure. So the question we have is, should we use effective overburden or total stress? Or total overburden? Well, you can use total overburden for total stress analysis, but often in design, you'll see that we just use Q prime, effective overburden, because it's conservative anyways. If I use total overburden, I get a slightly larger value, maybe just by 2 or 3 kPa, and that means that I have slightly more overburden pushing and suppressing bearing capacity failures. But since we're geotechnical engineers, we always want to be on the safe side, be conservative, so I don't think it's fatal that we use Q prime for calculations. My motto is that if you know the pore pressure, you should always use effective stress analysis. Then there also are practitioners and academics that feel you should never mix these parameters. So total stress should be all total stress, effective stress should be all effective stress. As long as we understand the limitations, advantages, and different views, then we can use whatever we like, as long as it's reasonable, right? So that's the effective overburden at the base. Now we have to carry out 2 sets of calculations. The first one is for total stress analysis for undrained conditions, okay? That's phi equals 0. Phi equals 0, then we get NC equals 5.14 if you flip back. And gamma is 0, and Q is 1, and you get a hydrostatic condition on this Kp is 1. So for shape factors, for SC, for undrained condition, or phi u equals 0, we have this equation. If you flip back, and you'll get 1.2. The base and width of the footing are both 1 meter. That's SC, and then you have the depth factor to account for the strength due to overburden, which is generally neglected in generalized bearing capacity equations. That's also 1.2, and then for undrained condition, DQ and SQ are also 1. So once we have these factors, we can dump everything back into our generalized bearing capacity equation here. So the bearing capacity in the short term, C would be Cu in this case, NC, SC, DC plus Q prime, and Q is Q, DQ. Because it's undrained, we don't have the unit weight component. So 25 was the undrained shear strength you're given. 5.14 is NC. You have 2 shape factors and depth factors, 1.2, 1.2. And here, for undrained analysis, you might be thinking, can we use the total stress overburden? Yeah, feel free to use it. Effective stress is more conservative in this case. It's smaller. As I said, if you perhaps talk to some practitioners or academics, they feel like for any equation you should go across all total stress parameters or all effective stress parameters. In this case, it'll just give you an extra maybe 2-3 kPa. Yeah, I'm going to use K prime because I know the pore pressure, and if I know the pore pressure, I should always use effective stress. That's how I view it, and it's more conservative, it's safer. So I'm going to use K prime in my example, and then NQ and then SQ, DQ are all 1, and this gives you 200 kPa. So this is your ultimate bearing capacity of in situ soil in the short term. So that's 200 kPa. Now, we have to also do drain analysis as well, or effective stress analysis. I guess it's not correct to call it effective or total stress analysis because we sort of mix the variables here, so maybe we should call it undrained and drained. Maybe that'd be less confusing. For the undrained analysis, as I said, you can use total stress overburden if you like. So, need a few seconds to catch up. I'm going to typeset everything up and upload it. So if you can't catch my scribbles or you're not fast enough to catch my scribbles, that's fine as well. It'll all be uploaded and checked out. All right, so we got 200 kPa for undrained condition. How about drained condition? For drain condition, we have to recalculate all our bearing capacity factors. And if you flip back a few slides, you'll see these expressions, so please do not be too shocked when you see these. We're given a friction angle of 25 in the question. That's where 25 degrees comes from. So NQ would be 10.6. N gamma, we also have to do a calculation. So once you know NQ, then you can calculate N gamma. And then we can calculate Kp. This is 25, so then you'll get a Kp of 2.46. This is probably the worst form to write Kp, right? If you're in an interview and they ask you, what's Kp, what's Ka, how do you remember? Well, the simpler form, the form that I like is usually, so that I can remember quickly if I'm asked, is 1 plus sine phi over 1 minus sine phi. I find this much easier to remember. And they ask you, what's Ka? It's just the smaller one, right? So it'd be 1 minus sine phi over 1 plus sine phi. And then if they ask you, what's the relationship between Ka, Kp, and K naught? It's a standard geotechnical interview question, right? Then you know that Ka should be smaller than K naught, should be smaller than Kp, right? So these are things you have to know automatically. These expressions you should know automatically as a geotechnical engineer, right? So just food for thought. I know some of you are preparing hard for interviews. So anyways, shape factors now for the drain condition. Well, if you flip back to a few tables, you'll see that we have this expression. And here's the not so friendly form of Kp. So S gamma and SQ is equivalent to 1.25, and then D gamma and DQ is given as such. We don't have the square here because it's the square root. So that's our shape factor. And then we plug everything back into our ultimate bearing capacity equation. So Qu is equal to 0.5 0.5 soil itself doesn't have any cohesion, so we only have two terms here. And since it's a drain analysis, we should endeavor to use effective stress parameters everywhere that we can. This will give you 282 kPa for the drained bearing capacity. So this is the ultimate bearing capacity of the in situ soil in the long term. Okay, so now we have two bearing capacities. You have one that's 200 kPa for the short-term condition, and you have a 282 kPa for the drained or so-called long-term condition. Now, as we mentioned, we use the smaller of the two to be safe, right? So Q ultimate long-term, which is 282, is evidently larger than QU short-term. Therefore, we know that short-term controls governs. Okay. So we have to calculate factor of safety now of the in situ soil. So we know the factor of safety is our short-term bearing capacity over the allowable, which we calculated in the beginning, the net bearing pressure. So, unfortunately for us, the factor of safety is only 1.18, which is less than the required 3. So, what does that mean? Well, we need to carry out over-excavation. That's not how you spell over-excavation, okay. Over-excavation and replacement is necessary. So we've already seen in the question that they've already replaced it. So this is just a check. Let's say they didn't replace it, then you have to check that your factor of safety is insufficient and you need to carry out replacements. Now replacement, if you remember the question, is a 2 meter by 2 meter into the page and only 1 meter thick for the gravel or fill material that they use. So this is only the first step. We just checked, is it necessary to do over-excavation replacement? And the answer is yes. Now we have to check the 4 failure modes with replacement. And lucky for us, we don't need to calculate the size of the replaced zone because it's given. So the first step is general failure within the replaced zone. So this is now very much in play. So the first failure mode is, will the replaced zone just fail by general bearing capacity failure? Well, the replaced zone, if you remember the question, is just gravel, right? Coarse grain gravel. So we probably don't need to do an undrained analysis. It's very pervious. We're talking about maybe 10 to the minus 2 meters per second, 10 to the minus 1 meters per second. That's how pervious it is. We don't expect that the rate of loading will be substantially high enough to cause undrained conditions. So the gravel, if you remember from the question, we can call the gravel 1, subscript 1. There's no effective cohesion, and there is 38 degrees friction angle, which is quite high. It's reminiscent of gravel. So let's check now after replacement. So again, we have to carry out shape factors, so NQ1 you remember, is this. We have to put in the friction angle for the gravel this time. So it's not the same as the last question where we only calculated these bearing capacity factors for the in situ clay, right? Now we have to put in 38 degrees. So if we plug in everything, we will get 38 over 2, E pi 10, 38. This will give us the NQ for the replaced area of 48.9. The next step, this is drained only, okay, because it's gravel, okay? It's very pervious. So N gamma 1 is equal to NQ1 minus 1 tangent 1.4 pi, not phi, and then we have 48.9 from above, minus 1 tangent 1.4, 38. This will give us 64.1 for N gamma 1. Shape factors now. For drain condition, we can use this expression, which will be given to you in a stressful exam condition. 1 plus 0.1 times Kp times 1 over 1 equals 1.42. Likewise, depth factors. Not squared because we square rooted it again. No. Okay. Times 1 over 1 is 1.21. It's 1.42. So we have all our shape factors, and we can pull our generalized bearing capacity equation out, plug in all our knowns, and we can calculate the bearing capacity of the replaced zone subjected to generalized bearing capacity failure. So in general practice, let's write out the equation. Effective unit weight. Footing is 1 meter, and gamma 1 is 64.1 times our two factors of 1.42 times 1.21 plus 15, which is our effective overburden. If you remember from the last slide, we don't need to calculate it again. Effective burden. Overburden has not changed. The question 48.9 for NQ1 has the shape factors and the depth factors, and we get a bearing capacity of 1,822 kPa. So since we only have to do drain, because this zone here is gravel, which is pervious, it's not like it's clay, we don't expect undrained loading conditions to occur. So the factor of safety is equal to 1,822 over our allowable load, or net bearing load. So this gives us a factor of safety of 10.72, which is much larger than 3, which is required. So we know we're okay for generalized bearing capacity failure through the replaced zone. So this mechanism has been checked. So out of the 4 mechanisms, we have 1 down, we have 3 to go. Generally, I think I would just ask for this much from you for an exam. The following 3 mechanisms, maybe I think it's slightly a little too much to handle, but let's go through it together. So the next failure mode is, I think, punching failure, right? So it happens when we punch right through the replaced zone, into and underneath the soft in situ soil underneath. So let's look at that together. We have to flip back and forth in the slides. What's that? So since punching failure through the replaced zone occurs in the soft soil, so that would be undrained. So we have to do undrained and drained analysis for punching failure. It's not just through the gravel, like the last example. Now it's through the gravel and into the clay, so we have to carry out both because we're unsure which one governs. Drained and undrained loadings cases are extreme cases, idealized cases. In reality, we must be somewhere in between, right? So that's why, as geotechnical engineers, we need to check undrained and drained. If you ask, is it really like this in reality? Yeah, it's probably somewhere in the middle. You don't really have a purely drained and undrained case. It's idealized for classroom theoretical purposes, okay? So punching failure through the replace zone. We must first look at undrained scenario. So I'm not going to keep on calculating the NQ and the N gamma because it's quite painful. I'm just going to write them out, and if you're not sure where it came from, it's from previous steps that's been calculated already. So we have replaced zone NQ1 equals 48.9, and gamma 1 is equal to 64.1. For the soft soil that we're dealing with, we know that phi equals 0. Soft soil is denoted as subscript 2 in all subsequent problems, and the replacement material is subscript 1. So these are well established from before. If you don't remember, this is also shown in the slide, the last slide, which is 29. So to carry out the bearing capacity calculation for punching failure, we have to refer to Meyerhoff and Hanna's, I think 1978 expression. Now, remember, to calculate punching failure, we need to obtain Q2 over Q1 ratios. So Q2 is the soft soil, Q1 is the replaced soil. Why? Because we want to get some sort of coefficient of punching, right? We know our friction angle of the soil, of the replaced material is 38, right? But the question is, what is Q1 and Q2? Now, if we look a few slides back, you'll remember that I mentioned that Q1 is C1 and C1 plus 0.5. And Q2 is more or less the same thing. For this particular failure mode of punching through, if you don't remember, it's something like this. This is the replaced zone here. We're worried about this punching right through the replaced zone, R, are also known as subscript 1, and then causing some sort of bearing capacity in the soft soil underneath 2. Now, when we carry out Q1 and Q2, you might be thinking, where are these expressions from? Well, why is there no overburden component? Well, this failure mechanism here for punching failure, it's really hard to define where the overburden would act for Q1 and Q2. So I guess that's why it's simplified, it's simply not shown. And by not considering the overburden, if you remember, it's conservative. Here we're really looking for a ratio, so it's not entirely consequential. So that's why if you look a few slides back, we have just these two expressions to get Q1 and Q2. Now, let's calculate Q1 and Q2. So Q1 is equal to 1.5 gamma 1 BF and gamma 1, which is, for the replaced sum, we don't have any cohesion or effective cohesion, so that term is 0 times 64.1, we get 641 kPa for Q1, and Q2 is the soft soil. For the soft soil, we use the same expression, except we don't have N gamma, because remember N gamma term is not needed for the Andre case, so then we can just calculate (129 kPa). So if we take the ratio of Q1, Q2 over Q1, you'll get 129 over 641. This will give you a Q2 over Q1 ratio of about 0.2. We know the friction angle of our replaced material is 38 degrees. So if we have 0.2, 38 degrees, this is 0.2, it's 0.2, 38 degrees. So if we mark it over, we would say we have a punching coefficient of about 4. That's our punching coefficient. And once we get our punching coefficient, then if you flip back to where we talked about punching failure, we can calculate the resistance due to punching failure. But before we do that, we have to calculate shape factors again. So SC has not changed. It's still 1.2. DC is slightly different this time because the depth is not the same as before, because we're going deeper into the ground. So it should be 0.2 plus DF plus HR. So the depth of overburden plus the height of the replacement zone. And this will give you 1.4 instead of 1.2, as in the previous example. And likewise, SQ equals DQ equals 1. Effective overburden has not changed. We can calculate again. Plus 1.4 is the depth. 20 minus 9.8 equals 25 kPa. So now we're looking at the effective overburden here. Now, with this expression in mind, what we can do next is we can calculate the bearing capacity due to punching failure. And this expression at the base is more or less the same as what we've been using before. This Q prime is at the bottom of the replacement zone, so we can just say R here. We have NQ, Q, SQ, DQ. Undrained shear strength is given in the question as 25, NC2 For undrained case, 5.14. Then you have your shape and depth factors of 1.2, 1.4. 25 is your effective overburden at the base of the replaced zone. And then you have 3 ones for the factors. And this gives you 241 kPa. And to calculate punching failure, we need our passive load on the side to resist the lateral punch out. So we have our punching coefficient Ks times 0.5, and this equation is given in a few slides back. HF squared plus gamma 2 dF HR. This is equal to the punching coefficients 4 that we read off the graph. Since this is a total unit weight, we'll do that 1 squared plus 18 times 0.6 times 1 plus 20 times 0.4 times 1. This gives us 115 kilonewtons per meter for pH. And once we have pH, then we can calculate punching failure resistance, bearing capacity. If you're not sure where this expression is, flip a few slides back to when we're talking about punching failure. This is after we've integrated assuming a constant Ks. Likewise, these expressions here, it's just this. This is simplified. We don't need the second term. If you calculate all the N gamma, NQ, and NC, you'll figure out why we don't need the second term. We calculated Ks equals 4. We plugged it in here, so we have 115 kilonewtons per meter into the pH. So that's punching failure resistance on the side. And once we have that value, what we can do is we have to calculate the weight of the replaced area first. So that's 20 times 1 times 1 times 1, and that's 20 kilonewtons. So this is the weight of the replaced area. And to calculate the resistance due to punching failure, this equation is also shown in earlier slides. We have U, P, which is the perimeter of your foundation. Minus the weight of your replacement zone over the area of your footing. So we just plug everything in. We know QB is 241 plus 4 times 1, because it's 1 meter by 1 meter by 1 meter, times 115 kilonewtons per meter run, times the friction angle of your gravel in the replaced zone, which is 38 degrees. Then you don't have any effective cohesion or cohesion at all. The weight of your replaced zone is 20, and the area of your foundation is only 1 by 1. So then you get about 580 kPa. So that's the undrained bearing capacity due to punching failure. And similarly, we also have to calculate that due to drained. It's quite repetitive, except we try to use effective parameters where possible. Again, I'm not going to recalculate all the bearing capacity factors because we did it in previous slides. NQ2 and gamma 2 were calculated as 10.66 and 6.77 respectively. This was on slide 28, if you're not sure where these are from. And we have to do the same thing, calculate Q1, Q2, Q2 over Q1 ratio. expression. I'm not going to write the expression out for cohesion because it's strictly unnecessary for Q2. So this is a drain case here. And Q2 over Q1 would be 34.5 over 327, giving you 0.1. So if you read off the same punching coefficient graph for a friction angle of 38 degrees, you'll get a punching coefficient this time of 2.5. On top of these, you have to calculate the shape and depth coefficients. S gamma, SQ is 1.25, and then you have to calculate D gamma and DQ. Again, we have to take the depth all the way down from the overburden plus the replacement zone here for the depth. For D gamma and DQ, and then you can calculate QB just like in the last undrained example. This is the effective overburden at the bottom of the replace zone. Then NQ to SQ DQ. So QB is equal to G minus 9.1 for the effective unit weights times BF is 6.77 for N gamma, 1.25 times 1.31 for the shape and depth factors, plus 25 for the effective overburden at the base of the replacement zone, NQ2 times your shape and depth factor again. This is 493 kPa. So QB is 493, but we're not done because we have to calculate pH, and when we calculate pH, then we can calculate QU, just like what we did at the top here for the drain case. Once we get QU, then we can compare drain versus undrained, which one is smaller, and we take the smaller one because we want to be more conservative. So we keep on going to finish this part off. This expression again is given to you in the slides. If you can't keep up, that's fine. I'll post the full solution on after. So this time our punching coefficient is 2.5 instead of 4. We have 0.5 times effective unit weight 20 minus 9.8 times the height of the replacement zone is 1 squared plus the effective unit weight of the second part is 20 minus 9.8. Depth is 0.4 minus 9.1. Or it should be 18 actually for the second part. Okay. 10 times 6 1 plus 20 minus 9.8 times 0.4 times 1 equals 50 kilonewtons per meters run. And we can just finish off now by calculating the weight of the replacement zone. The weight of the plug, particularly. Kn, and bearing capacity resistance is again calculated the same way as the undrained part last time. Area is 1 times 1, and then you get the drain case bearing capacity of 639 kPa. So if we compare the drain and undrained case, undrained is less than QU for drained. Therefore, short term governs. So we can calculate the factor of safety for short term. We know it's 580 kPa over the allowable 170. You have a factor of safety of 3.41, which is still greater than 3. So for punching failure, you're okay. So we only have to check 2 more failure mechanisms. They're a little simpler than punching. But I think we can take a short break, maybe a 10-minute break, and then we can finish off this problem. For those of you that came in late, I'll give you another extension for your assignment of 2 weeks, because I think there's more information about the surcharge. If you submitted it, did some of you submit already? I'll release it back to you. We'll give you an extension to give you more information. Did some of you submit already? Was it due today? No, okay, yeah, that's fine. For those that submit, well, I'll release it back to you and we can give you another 2 weeks. In case you came in a bit later and you missed that earlier.
那這係佢呢個 part 嘅喎，copy 之後要學埋。我俾我啲朋友係啊，即係我都有啲情況。我知道之後就理論上佢都係要可以呢個嘛試下，跟住就出嚟。乜仲 call 你哋得咯？最緊要你講先。我都要抄。跟住又八盤就俾佢嘗試，係從嗰時好似結果得。
All right, let's carry on. So, yeah, the last part here, or second last part, is to calculate Taylor distributive foundation. We talked about the importance of finding theta, because theta is your distribution angle. So, to find theta, we generally just refer to design guidelines, and you can get 30 degrees if you look at the specifications of the previous slides. That's where I copied this excerpt from. Nevertheless, if you look back a few slides, you'll also see that we can calculate the distributed lengths once we know the distribution angle for both length scales of base and length as tan theta. And we know that we will get a new distributed length of 30 degrees, and this is about 2.15 meters. And this is a little too precise for lighting, so to be conservative, we can reduce this to just 2 meters. Smaller area means higher stress anyways. So we can take L prime, B prime is equal to 2 meters. And the effective overburden stress at the base of the distributed footing would be calculated in our previous parts. It was 25, right? 25 kPa. That's the base of the replacement. Sorry, this would be subsequent R. It was 25 kPa. So again, based on this dimension, we have to calculate drained and undrained condition again. So for undrained condition, we have to calculate shape factors, SC, SC is 1.2, DC is also 1.2 in this case. And SQ was 1, DQ also equals 1. The ultimate bearing capacity due to the distributed foundation. So this is the same as the first failure mode, except we use a slightly different length scale from distributed loading. Is CU, NC2, SC, DC plus Q. Effective overburden at the base of the replacement zone should be R. NQ2, SQ, DQ equals 25, 5.14, 1.2, 2 plus 25 times 1 times 1 times 1 equals 210 kPa. So the ultimate bearing capacity, QU, if you flip back a few slides, is calculated using this expression. This is the new length of our distributed footing. 760 kPa. That's for the undrained case. And likewise, we have to do the same calculation for the drain case. So for the drain case, this is 1.25, and then gamma, dq. Depth factors are we take the depth all the way to the bottom of the placement zone, so it's df plus hr plus 1.1 then squared, which is 2.5 plus 25 over 2 times 2 equals 1.16. So now that we have our shape and depth factors, we can calculate the bearing capacity again. Ultimate bearing capacity is calculated the same as above. So we have two QUs for drain and undrained. You can see it's 760 and 1,907 kPa. We take the more conservative of the two again. So we take the 760 to get our FOS. So 760 over allowable 170. This gives us about 4.47 factor safety, which is still larger than 3. So for distributed loading, we're still okay. So just to tidy up the example, I know this is painful, but the last one here is punching of the replacement zone through the in-situ soil. This one is less painful, I promise. And that's the last mechanism we need to check, and then we can compare all 4 mechanisms in terms of factor of safety. Okay, so the last mechanism we also have to check for drain and undrained is we know that the length of the replacement zone is 2 meters. I'll post these onto Moodle later, but the issue is anyhow, let's look at the undrained and drained cases first. Undrained. So we would calculate the Q2 over Q1 ratio in the same manner, but since KS, in this case, you have to flip back to look at the fine print. This is at the bottom of slide 24. So KS is the coefficient of punching shear around the perimeter surface replace zone. We can estimate this value by assuming Q1 equals Q2. And using the friction angle, of in situ soil, there are a few constraints though. Ks must be larger or equal to K naught, and we know how to calculate K naught. So for NC soil, we use the Yankee equation. We know K naught is equal to 1 minus sine phi. So I'll write this note as well because we need to use it later. So QU should be the lesser of the calculated shear shear resistance deduced from two sets of parameters, from C1 and phi dash 1, or C2 and phi dash 2. So this is a slight precondition at the bottom of slide 24, if you flip back and look at it. Also, I guess you probably should know this equation, Yankees equation. If someone asks you how to calculate at-rest earth pressures, this is for NC clays only, right? If it's for OC clays, you probably wouldn't use this. But I don't think anyone will ask you about OC clay. But at rest earth pressure, 1 minus sine phi. We call it the Yankee equation, J-A-K-Y. So for the undrained case, based on this wall of text here, we know that we can make these assumptions. Since Ks is larger than Yankees equation, and also we have shape factor calculations again. Depth factors. SQ and DQ are equal to 1 for undrained case, and we can calculate QB as follows. Effective stress at the base of the replaced zone. This is 25, undrained shear strength. That's 5.14 for NC and drained. 1.2 times 1.2 plus 25 for the effective overburden at the base of the replacement zone. And you have 3 ones for the shape depth factors. So QB is 210 kPa. Passive force is calculated using the same expression as the punching failure. this case, our punching coefficient is 1 because of the wall of text on the right. This is equal to 28.8 kilonewtons per meter run. And then we can calculate two QUs here. So QU1 and QU2. The replaced area is slightly larger, so it's 4 times 2 meters rather than 4 times 1 meter in the last example. This is 180 kilonewtons. And then QU2. Is 200 kilonewtons. So we're asked to take the lesser here of the two resistance based on the two sets of strength parameters. So we know that we should be taking 180 kilonewtons instead of 200. So we know the weight of the replaced zone now is 20 times 2 times 2 times 1. That's 80 kN. So we can calculate the ultimate bearing capacity as QB ARZ over AF plus QU QU, we take the 180 minus 80 for the weight of the replaced zone over foundation size of 1 meter squared. And for the undrained case, you have an ultimate bearing capacity of 940 kPa. So that's for the undrained case. And last but not least, I promise, this is the drain case. The drain case is calculated exactly the same as the undrained case, except we use, well, drain or effective parameters where we can. So for the drain case, the steps will be more or less repeated. So Q2 over Q1, we can make the same assumption, is equal to 1. Friction angle, however, is 25. Will give you a punching coefficient of 3.7. S gamma and SQ, I'm not going to write the expressions out anymore, will be 1.25. D gamma is equal to DQ, 1.16. QB is the base of the replacement zone, and gamma 2 is 6.77, shape factor 1.5 times 1.16 plus Vector stress at the base of the replacement zone is 25 kPa. NQ is 10.66, and then you have two shape and depth factors of 1.25 and 1.16. This will give you a QB of 487 kPa. pH1 is equal to Ks 1.5 gamma 1 HR squared plus gamma 2 prime dF HR. This would give you a lateral force of 3.7 times 0.5 times 20 minus 9.8 times 1 squared plus 18 times 0.6 times 1 plus 20 minus 9.8 times 0.4 times 1. You get 74 kilonewtons per meters run. Then again, we can calculate the two QU1 and QU2. I'm not going to write the expressions out, and we take the lesser of the two, which is 276. So you have two sets of strength parameters, and we take 276, and we can calculate the weight of the replacement zone. Last but not least, to calculate the ultimate bearing capacity due to drain condition. Seven times 2 times 2 over 1 times 1 plus 276 minus 41 over 1 times 1 is equal to 2,183 kPa. And we know now that drained, our long term is 2183. And short term is 940, so we take the smaller one. So for the FOS, we take 940 over the allowable load of 170. This gives us 5.53 for factor safety, which is larger than 3. So we're okay for the last mechanism. So painfully, we've looked at all 4 mechanisms for drained and undrained. I guess for exam purposes, I want you to just be able to calculate the bearing capacity before punching failure, before and after replacement. The rest of this is just for completeness if you have to calculate punching failure. So in summary, let's summarize this very long example. We know that there were 4 failure modes. The first failure mode was general failure in the replacement zone. That's the first one. The second one is punching failure. Through the replaced zone. The third one was failure of the distributed foundation. Four is the punching of the replaced zone into the in situ soil. So for the undrained case, drained case, and then the FOS. So in summary, we didn't have to check undrained or just through the gravel. This is, these are of course your QU and KPA. Factor of safety was this, it's very high, and then we have 580, 639. We took the smaller always. So this was the summary of our example. What we see is that we survived all 4 failure modes. This one here, punching failure through the place zone, was perhaps the closest to 3. But generally, this is how you would check a shallow replacement. But like I said, for your examination purposes, this is really the only one that I need you to know how to calculate generalized air capacity failure. But you do have to appreciate that you have to check a lot of things to make sure your shallow replacement works. So yeah, in summary, this is how you do replacement, and in the last 2 slides here, we just have some additional information on how to select fill material. I guess these are quite obvious. You should not pick anything with organic matter that's highly compressible. Depending on the region, you don't want to pick anything that's susceptible to expansion or collapse. Nothing that has a high LP or liquefaction potential. I guess these are quite obvious. Shallow excavation, as we mentioned, is quite expensive, and you don't want to replace too much soil. You don't want to cause lateral instability and need shoring. You have to think about sensitive receivers nearby, pipelines. You have to be able to dispose and deliver any fill material. If you have a high water table, you probably don't want to do this, otherwise you need to do water. And anything in excess of 6 hours for open excavation, you probably don't want to deal with. In that case, you probably want to do 2-to-1 berms. So these are just a summary of some considerations for shallow excavation. So that's all I want to talk about for shallow excavation. The next topic that we'll transition to is deep replacement. For deep replacements, use this. So up to this point, we've looked at shallow replacement, but there's also something called deep replacement. Deep replacement, as the name sounds, well, you're replacing soil by digging deep into the ground and then replacing it with something more competent. Shallow replacement, you can still do calculations. As you see, your hand is probably tired by now. Deep replacement, it's highly empirical, but you still need to understand that it exists. Some examples are stone columns that we use for Disneyland in Penny Bay. We installed a lot of stone columns in the ground. Some parts of Hong Kong where we support seawalls, we also use stone columns. These are examples of deep replacement in the ground. I'll go through the different forms of deep replacement in the following module with you. Likewise, before we talk about each type of ground improvement technique, what are the expected outcomes for this module, you should be able to identify what are the suitable conditions to carry out deep replacement. What's the mechanical advantage of adding composite columns in the ground? We'll talk about that. There are some very similar terms: vibro replacement, vibro displacement. What are the fundamental differences between the two approaches? We also refer to terms such as area replacement ratio. You've probably heard of these. Also, equal stress, equal strain conditions, stress concentration ratio, how much stress are my columns taking relative to the soft soil around it. If you work in ground improvements or you've had some chance to work at the third runway system at the Hong Kong International Airport, then you probably hear these terms all the time: area replacement ratio, stress concentration ratio. Also, we'll look at some very brief methods to describe the stress distribution resulting from composite deep replacement, and also what we mean by equivalent stiffness of a reinforced foundation. Again, I think for our course, I think we've covered most of the painful calculations. You can just sit back a bit more, because some of these methods, such as chemical ground improvement, these are highly experience-based methods, but you still need to know about them, because if you're on a construction site and someone says stone columns, I mean, what are stone columns, right? How do you model them in Plaxis? We won't talk about that, but at least you need to know what stone columns are, or what deep cement mixing is. So the next couple modules on deep replacement, chemical improvement, there's less you can really calculate. It's more experience-based, and you usually bring in a specialist contractor to do it. And this specialist contractor has a lot of experience in Hong Kong and probably can do a really good job in Hong Kong. But if you bring this contractor overseas, not so much, because they don't understand the geological conditions. So we'll mostly be sharing with you about concepts in the forthcoming modules until the end of this particular course. So let's get started with deep replacement. We still have some time today in the lecture. There are a multitude of deep replacement techniques. In fact, there are so many that we have to use the schematic to confuse you. There's particularly different terms we need to acknowledge. There are two main types of deep replacement. One type is called excavation deep replacement, and the other is called displacement. In excavation, you're normally trying to remove material by flushing using high pressure air, high pressure water. Displacement, you're trying to jam better soil in the ground to push problematic soil aside. You're squeezing it away from where you're injecting the soil. And if you look at the slide, there's red and green. Red are excavation related methods, and displacement are methods where you're really forcing new soil into the deep ground and pushing problematic soil away. Regardless of whether it's excavation or displacement, we are still trying to achieve the same thing: forming a systematic array of columns in the ground. And when you have a lot of columns in the ground, we call this a composite foundation. And you can probably imagine already, the density of the columns in the ground will affect how stiff the composite ground behaves. Also, it'll affect how expensive your foundation is. So a lot of the composite foundation behavior really depends on the spacing between columns. So this is very similar to deep dynamic compaction we talked about earlier. And I do want you to think about what the difference is between deep dynamic compaction and deep replacement is as we progress through this particular module. Most of these things are in column forms because if we use columns, we can reach much deeper depths in the ground. That's why we call it deep replacement. And the overall objective of deep replacement is more or less the same as the other types of ground improvement. We're trying to improve strength, stiffness. If you're trying to place some loads on it, increase bearing capacity. If you use a very pervious soil, gravel, sand, you provide drains to increase or decrease the time required for consolidation. In places susceptible to seismicity, we want to decrease LP, liquefaction potential, which is when your effective stress goes to 0. Stone columns sound interesting, but requires stone and sand, right? Which is quite expensive these days. We will talk about a case study, as I mentioned, in Penny Bay. Stone columns can sound scary when you don't have a lot of local experience. We'll talk about some potential failure mechanisms, failure modes of stone columns, how to make them stiffer, how to make them softer. So that's what we'll talk about. Now, I'll try to cycle through this slide a little bit. So at the top left here, we have the first method called vibro replacement. So it's an excavation approach where you're injecting some sort of water or slurry to flush out problematic soil. And after you flush it out, then you can replace with sand or gravel. We'll look at some field videos of this happening later so you can understand how it looks like. That's vibro replacement. So replacement means you're removing and replacing. The next one you see here is vibro displacement. Vibro displacement, you're basically using something that has a vibratory device that vibrates into the ground, and then you can feed gravel or sand down, and you basically squeeze the problematic soil aside to form columns. There are two types of feeding. At the top here, you can see a term called bottom feeding. That's when you inject the gravel or sand from bottom up. Another type of feeding is if you form the hole, and then you have excavators just to push gravel into the hole from the top. We call that top feeding. So there's bottom feeding and top feeding. And in Hong Kong, you might be thinking whether stone columns might be useful for all the reclamation projects we have. It might be. There's some interesting ideas. We're trying to build a lot of caverns to put data centers in, wastewater treatment facilities. So when we build a cavern, we need to do blasting, right? We need to blast the rock, excavate it. So the question is, what do you do with this rock after you blast it? Well, what if you could blast the rock so that you can create sizes that are ideal for stone columns, and you can recycle it and sort of create some synergy between caverns and stone columns. So from caverns to reclamation. So this is one of the things that the Geotechnical Engineering Office is interested in. I'm not sure if you've heard about it, but the reason is it reduces the carbon footprint. If you have a cavern really close to where you plan to reclaim land, then you can reduce the embodied carbon footprint, right? You don't have to transport the rocks very far. And for us in Hong Kong, we already don't have a lot of gravel and sand. We don't have a lot of quarries that can mine sand and rock. So if we're purposely building caverns, then we might as well try to blast or break down the rock into sizes that we can use. Of course, there's a bit of research that needs to be taken. What size of rock do you need to form a good stone column? It can't be too big, right? Otherwise, it's just one rock inside a hole. So how do you form these force chains that can form a very composite stone column? It's not easy to blast rock to a particular size, right? you need to plan on what size you need. So this could perhaps be an interesting idea. If you go for an interview, they ask you, what are some techniques you see that we can, or sustainable techniques for ground improvement? You can perhaps say that we can use the rock from caverns, break it down into ideal sizes for stone columns for reclamation. This will decrease the embodied carbon footprint, and it's basically two birds with one stone. I think. Then we don't have to think about what do you do with the rock after you blast it. Right? So stone columns is definitely one of these deep replacement methods. Sorry, I went off on a tangent. In terms of vibro displacement, you vibrate a probe into the ground, and if it's granular material, it's easy to do because vibration destroys granular contacts, and you can sink this probe down, and once you get to your formation level, you start, in this case, bottom feeding and lifting the probe up, and you can get stone or gravel columns. Likewise, if you want, you can also inject concrete and not just rock and gravel to form concrete columns. That's also displacement and by bottom feeding. So you see these two examples here, vibro displacement by gravel and by concrete. So I see we're out of time. So we'll carry on with deep replacement in our next lecture. So again, you will have an extension on the assignment. I just want to make sure that we have given you all the hints apart to solve. We'll update this on Moodle. I'll see you next week.
好好知啊！哎呀〜